Scientists use a technique called sonification. They take real measurements, like changes in light, radiation, magnetic fields, or particle density, and convert those variations into frequencies we can hear. Nothing is invented. The patterns come directly from the physics. We will start our journey from the sun. What you are about to hear is the data captured from the Parker Solar Probe. It measured plasma waves and magnetic fluctuations of our star, and those signals were converted into audio through sonification. The result is a translation of solar activity into frequencies we can hear. Listen. Moving on, we are now approaching Earth. What you're about to hear was captured by NASA's twin Van Allen probes on September 5, 2012. This sound is produced by very low-frequency radio waves, generated either by lightning strikes or by excited electrons spiraling through the Van Allen belts, two vast regions of radiation surrounding our planet. We will now head to Mars. This sonification was created using the SuperCam instrument aboard NASA's Perseverance rover, just about 18 hours after landing. At that moment, the microphone was still stowed on Perseverance's deck, so the audio sounds muffled. Now let's head to Jupiter, the giant. What you're about to hear are radio emissions collected during Juno's flyby of Jupiter's moon Ganymede on June 7, 2021. Now we turn our warp drive towards Saturn. What you're about to hear is the interaction of plasma waves traveling between the planet and one of its moons, Enceladus. We will now leave our solar system and head toward the Helix Nebula. What you're about to see is a Hubble image of the nebula converted into sound. In this sonification, color is mapped to pitch. Red corresponds to lower tones and blue to higher ones, while brightness controls the volume. Red regions reveal hydrogen and nitrogen, and blue regions trace the presence of oxygen. We will now travel thousands of light years away to another iconic and very famous nebula, the Butterfly Nebula. This sonification is scanned from left to right, and the vertical position is mapped to pitch, meaning that light near the top of the image produces higher tones. Now we will leave our galaxy and head toward Hoag's object, located more than 600 million light-years away. As we aim our camera toward this distant galaxy, you will notice the stars of the inner Milky Way begin to stretch as our speed increases. We will turn our camera slightly so we can enjoy the Milky Way's majestic view, and then readjust our warp drive toward our destination. We are now entering intergalactic space, accelerating our warp drive to colossal speeds until entire galaxies rush past us and we begin to approach our destination. Between galaxies lies one of the emptiest regions in the universe. Intergalactic space contains only a few atoms in every cubic meter, far emptier than any vacuum we can create on Earth. Here, distance loses all familiar meaning. Light itself can take millions of years to cross the void. Hoag's object is a rare ring galaxy, a nearly perfect circle of stars surrounding a bright core, with almost nothing in between. In this sonification, a clockwise radar scan transforms the image data into sound. Bright regions are represented by louder volume, and light farther from the center produces higher pitches. We are now heading toward the Mince Galaxies, a gorgeous pair of colliding galaxies that will eventually merge into a single system. They lie about 300 million light-years away in the constellation Coma Berenices. It's incredible to realize that all these small, bright dots are galaxies, not stars, each with its own constellations, systems, and planets, and perhaps even countless civilizations at different stages of evolution. As our speed increases, you will notice entire galaxies rushing past us at incredible velocities until we reach our next destination, the Mince Galaxies. There they are, that bright dot ahead of us, growing larger and larger as we approach. These galaxies are on a collision course and will eventually merge into a single system. Now stop for a moment and imagine the view a planet here would have. In this data sonification, scientists mapped brightness to both volume and pitch. Brighter regions sound louder and lower pitched. From the quiet wind on Mars to the electromagnetic storms of Jupiter, from distant nebulae to colliding galaxies, every sound you heard is a translation of real cosmic phenomena, a reminder that even in silence, the universe is full of music or even bizarre sounds. Until our next journey, traveler, and please don't forget to subscribe to our channel and help us create more scientific content like this.